personal. And I hope I will be able to cover all these topics during the 2 lectures. So on the experimental side, when I remember when I was a young PhD student in the early 90s, when people were referring to functional oxide thin films, that was mainly referring to micrometer thick polycrystalline samples. And that's quite amazing, because I remember some schools at the MRS in Boston at that time, and thin film was really something that was not what we call thin films today. So it was really what we call thick films. And then at the end of the 90s, beginning of the 2000s, I think there were dramatic improvement in the epitaxial growth of functional oxides, so that now we can reach monocrystalline, nanometer thick films and heterostructure with really an atomic scale control and sharp interface. And that's really a dramatic change that happened during that period, end of the 90s, beginning of the 2000s. And this was a very important move, in the sense that if you can grow sharp interface like that, you really create new opportunities at the interface. And indeed, when you create such interface, you can imagine that you will couple the different degrees of freedom that you have in your solid, like the lattice distortion, of course, the spin, the charge, the orbital. You can couple that through different materials, playing with different possible strategy, like you see engineering strain, or producing a symmetry breaking, making electrostatic coupling between the different layers, producing charge transfer or frustration at the interface. And this was a very step-by-step, I would say, opening the way to the rational design of new materials. And since, I would say, 20, 25 years, the perovskite cubic structure is now considered as a Lego block, and you can now take these different materials, different Lego blocks, and build them together in order to create new artificial materials. And that's very exciting. And through this kind of combination of materials that you can really control nearly perfectly, you can try to do different things. And basically, the new opportunities at the interface are quite different, but are very interesting. So on the one hand, you can achieve fine-tuning of existing bulk properties, for instance. So you have a property that is already there at the bulk level, but understanding the origin of this property, now you can try to tune it. And that's something that has been realized, for instance, through the strain engineering of ferroelectrics. I am reporting just here one of the seminal paper doing that on biome titanate, where you see that when you grow a biome titanate on top of a substrate, if you can adjust the lattice constant and tune the in-plane strain of the film, then you can tune the phase transition temperature. And so you can basically move by hundredths of Kelvin the phase transition temperature of biome titanate. You can even make strontium titanate ferroelectric under strain engineering, and there are a lot of stories like that. This applies also to other kind of transition, like recently, together with Manuel, we achieved some kind of tilt control of the metal insulator transition in nickelates. Again, if you take a nickelate material, and I will discuss a bit at the end of my talk the origin of the metal insulator transition in these materials, but then you will see that this transition is closely related to the amplitude of the rotation of the oxygen cages. And now if you can put some interface layer that allow you to achieve some control of the tilt within the material, then again, you can tune basically the metal insulator transition temperature by a substantial amount. So here, basically, what we do is tune something that is existing, but then you can also see at the interface the emergence of totally new phenomena. And I'm just reporting here two cases that you probably know. One is this appearance of the two DEG at the LAO-STO interface, where you take two band insulators, you put them together, and then spontaneously you see a two-dimensional electron gas appearing at the interface. So this has been rationalized from the polarization discontinuity that you have at the interface, but this is clearly something that shows you the importance of creating interface. Another phenomenon that maybe you don't know is the appearance of hybrid improper ferroelectricity in lead titanate, strontium titanate superlattices. That's the work we did with Jean-Marc Triscone from Geneva, who is one of the organizers of the school, where we showed that when you create some superlattices alternating lead and strontium titanate, due to the change of symmetry, now you can achieve some coupling between the oxygen rotations in these materials and the polarization and produce what we know they call hybrid improper ferroelectricity. So that's really something new as well that was not present in the bulk material. And then this interface and these thin films also offer the possibility to synthesize materials that are not easy to grow as bulk nanocrystal. And I think it's mainly the case for nickelate. So it's very difficult to grow them at the bulk level, but it's more easily accessible as thin films. And then also you can stabilize metastable phase that are not achievable in bulk materials. And I'm thinking, for instance, here at the T phase of bismuth ferrite that you can get under epitextual strain, and that has some distinct property from the usual phase. So these interfaces are really creating new opportunities. And we have to realize that in the functional oxides, many of the properties are related to phase transition and appearance of distinct orders. So you can have in this material some ferroelectric orders, like in barium titanate or lead titanate. You can have antiferrodistortive orders, like related to the rotation of the oxygen case. So these are mainly appearance of structural distortion, but you can have also magnetic phase transitions, ferromagnetic, antiferromagnetic, appearance of spirals, and you can even have electronic phase transition, like charge ordering in nickelates or orbital ordering in the manganites. And so these materials are very rich. They are very useful for many applications, but many of these interesting properties that we want to use are related to phase transition. And so the idea is to reach some kind of rational design of interface for exploiting these properties, and in particular in tuning basically the phase transition temperature, for instance, in order to get it in the right temperature range. And of course, if you want to rationalize this, you need to get to have some microscopic understanding of this phenomena. And what is very important also is not only to focus on the interface itself, but already to get some understanding at the bulk level. If you know what are the key ingredients of the phase transition, then you can think about how to implement some modification of that due to a rational use of interface. And of course, doing that will require the possibility to model large systems with all the relevant degrees of freedom, and you want to do that with sufficient accuracy and predictive power. I would say when I was working in the 90s and I was looking at people doing thin films, so these thick films, I would say, there was no way for me to help them. Know that people are able to grow a very nice, nearly perfect interface, basically the kind of things that can be achieved experimentally is much closer to what I can model from first principle simulations. And so this has really initiated a discussion between theorists and experimentalists, because nowadays we can really address similar systems. And of course, I would say the kind of thing we can get from theory is very useful to basically make progress in the rational design of interface, but reciprocally, of course, the fact that no experimentalists can really grow so perfect structure is very important for us as well, just to probe our theories and to see to which extent they are right or completely crazy. So if we want to help experimentalists, we need to do some predictive calculation. And I would say that at the first principle level, density functional theory has become a standard tool. This theory is very interesting in the sense that it allows the self-consistent treatment of electronic and ionic degrees of freedom together. And in many cases, it is predictive. It's becoming so popular nowadays, and it was already at the end of the 90s, but it's even more true nowadays, that Walter Kohn got the Nobel Prize of Chemistry in 1998 for this theory. And for instance, if you look in PhysRev B, I think if you look at the most cited papers in physical review, I would say in the top 10 papers, probably 5 of them are referring to first principles theory within density functional theory. So this theory is nowadays something that everybody is using, sometimes as a black box, sometimes more smartly, but it is really, it has really become a standard. Of course, it has some drawbacks. It's not perfect for everything. It is often predictive, but not often. For instance, if we look at band gaps, they are not properly predicted by DFT. So for instance, if you look for materials for photovoltaics, for instance, you will need to go beyond that. And there are some approaches like the GW approach that allow you to make better predictions. Also, if you look at materials with strong correlation, as some oxide we will discuss today, of course, you have some limitation in DFT, and maybe you will need to go to more advanced approach like DMFT. And I'm referring here to the lecture of Antoine Georges that started yesterday and will continue to follow today. But typically, DFT is a starting point for this more advanced approach. So it's really something that is important because it's a good starting point for more advanced theory. But there is another kind of limitation to density functional theory. It is that it is limited to short time and short length scales. If I look here in terms of time and size of the system, you will see that first principles theory addresses a very small part of this diagram here. So it means we are limited in terms of size of the unit cell of the system that we can model to few hundreds, eventually thousands of atoms, but very small sizes in terms of angstrom. And also in terms of time scale, we are limited, I would say, in practice to few picoseconds. So it's really the bottleneck of first principle simulation is that it is limited to small system and time scale. And basically the bottleneck in this calculation is the quantum mechanical treatment of the electronic system. So the hope, of course, now is to go larger scale. If we want to address interesting questions from the experimentalists, if we want to look at domain walls, at, I would say, very, at phase transitions, for instance, to put temperatures and things like that, okay, we need to go beyond first principle density functional theory. It's not because the density functional theory is not able to treat that. In principle, we could address phase transition directly from density functional theory, and you can do DFT molecular dynamics. It's just the fact that the computation are so heavy that in practice, you are restricted to too small system and time scale, and you cannot really model this phase transition in an efficient way. So the idea that we have is to do some kind of multi-scale approach and to use what we call nowadays within the community second principle. It means that we want to build effective models that are restricted to a subset of interesting or relevant degrees of freedom, and with parameters directly fitted from first principles. So the idea is to keep the predictive power of first principles by saying, okay, we don't need experimental input. We can access to the microscopic quantities of the model, but instead of treating all the degrees of freedom at the quantum mechanical level as we would do in DFT, we will try to restrict to smart, effective models, but still in a first principle spirit where everything is computed and nothing is adjusted empirically. And so we can go from this first to second principle, and from this second principle, we can even go beyond and to build some Landau theory. And I will basically address these two, I would say, a kind of second principle model in my talk today. So just to summarize here, I would say that to give you a flavor, that first principle, at the first principle level, sorry, DFT has become a standard. It has no mature software. And when I compare to what was happening in the 90s, for instance, when I started my PhD thesis, there was more or less one code in each lab, and it was a homemade code that was developed locally. Now people have defined standards. We have some big codes. I will say a few words later about that. And these codes are really mature in the sense that now we can really do what we call high throughput calculation, and I would say we can automatically compute many properties of materials in automatic way, I would say, without even human involvement. So the machine can do the job, basically. Of course, even if this kind of approach is now broadly used, there are still two needs, I would say. The need one is to go more accurate. Of course, we need to improve. DFT is not a method that can do everything perfectly. So we still need to develop new functional to go beyond DFT, developing GW, DMFT, other techniques. But then there is a second need is to go larger scale. And going larger scale is the topic of my talk, I would say, today, and is to do it in a second principle framework. And I will define various approaches for doing that, because I would say that at this stage, contrary to what happened for first principle, where a standard approach have been defined, there is not yet a standard way to do second principles. And this is probably something that will keep us busy for the next decade. And I think this is a very important step forward that we need to do to access problems like domain walls, fermions, structural coupling at interfaces, charge transfer, finite temperature. So there is a huge demand behind this, and we are, of course, working on this. And so probably the two kind of lecture you have at this school are just addressing, like the one of Antoine and mine, are basically addressing two important issues nowadays, to go more accurate or to go larger scale. Okay, so that was my introduction just to motivate what I will present today. And the first part of my talk here is about density functional theory. This is something that is nowadays very popular, and probably you know already a few things about density functional theory, but since it is not a school for theorists, I thought it's maybe good to just to remind the basic principles and also to see what we can get and learn from such an approach. Okay, so let me start from the very beginning. I will go relatively quickly through the different concepts here, but I think it's good just to know what we are doing. Even if we know, I think it's good to remind us what we are doing. So materials are interacting electron and nuclei. And so basically, if we want to study the properties of material, and that's the dream of first principle simulation, is basically to address the properties of this electron and nuclei from their quantum mechanical treatment. And so solving basically the Schrödinger equation associated to this interacting system, basically we should get the energy and the wave, many-body wave function of the system. And the Hamiltonian is basically relatively simple because it includes, of course, different contribution, kinetic energy of the nuclei, the interaction energy between the nuclei, the kinetic energy of the electrons, the interaction between the electrons, and the interaction between the electrons and the nuclei. So basically, the kinetic energies are defined through the usual operators, and the interaction between these particles are basically electrostatic energy. So in my convention here, I will refer to the position of the electron as a small r and the position of the ions or the nuclei as a capital R. And this notation in bold means that I consider all the coordinates of all the electrons and all the nuclei together. So it's a set of coordinates for all the nuclei here and a set of coordinates for all the electrons. And so when we look at this, it looks relatively simple, but what is very complicated is that we have here a many-body wave function. And if you consider a solid with an enormous number of particles, basically it's totally impossible to solve this equation. So there is a first approximation that is commonly made and that we are making when we do this DFT calculation is the Born-Oppenheimer approximation. This is relying on the fact that the mass of the nuclei is much larger than the mass of the electrons, basically a factor 2000. But when you look back here in the different terms, you see that the mass of the nuclei is appearing at the denominator here. And so if this mass is large, so it means that this term here is eventually negligible in comparison of the others. And so basically the Born-Oppenheimer approximation is just to spread this kinetic energy term from the rest of the Hamiltonian, and the remaining part that we have here is what I call the Born-Oppenheimer Hamiltonian, and I will refer to this Born-Oppenheimer Hamiltonian as HE plus I. And what is very interesting when you neglect the kinetic energy of the ions here is that when you look back at the different terms here, you see that the kinetic energy of the ions is the only term where you have a differential operator acting on the position of the ion. So if you suppress this, then you see basically that the position of the ions becomes a parameter of your Hamiltonian. And so basically here, you need now within the Born-Oppenheimer approximation to solve a Schrödinger equation like this, but you see in which now the position of the ions are appearing of a parameter of your Hamiltonian. So it means that it's still appearing explicitly, but you can solve the problem at fixed ionic position, and then you will basically have to solve what is the ground state of your electrons at fixed ionic position. So this means, in other words, that you assume, because the mass of the ions is much larger than those of the electrons, that for any position, so if the mass is larger, they will move more slowly, basically. And so you assume, basically, in this Born-Oppenheimer approximation, that for each ionic positions, basically the electrons are in their ground state. And so they will automatically adjust to the position of the ions. And the Born-Oppenheimer energy is basically a potential energy for your ions, and it contains, of course, the kinetic energy of the electrons, the interaction of the energy associated to the interactions of the electrons together, the energy of interaction of the electrons within the network created by the ions, and an energy of interactions between the ions. But of course, if now you decide that the position of the ions are a parameter, then for any kind of position of the ions, you can estimate what is this term. So this term basically is a constant term that you can estimate for any position of these ions. So it means that when you solve this, basically, you can estimate this part separately. And what you need to determine is basically these things here. And then it means that you can recast this Born-Oppenheimer Schrödinger equation here in terms of an electronic Hamiltonian here that will neglect basically the interaction of the ions together because it is a constant term. And then you can basically find the ground state of your electrons by simply considering this electronic Hamiltonian here, where you take into account the kinetic energy of the electrons, their interactions together, and their interaction with the nuclei. And that I will refer to the electronic Hamiltonian. It's basically the Hamiltonian where you neglect the kinetic energy of the ions, and you also neglect basically this thing here. It doesn't mean that this term is not important. When you will estimate the Born-Oppenheimer energy, you will add this term, of course, but the value of these three energies here can be get from this by solving these equations here, where basically the position of the ions are still appearing, but as a parameter. And since they are parameters, in the following of my talk, I will drop the notation of this. So probably you are very familiar with that. But when you work within the Born-Oppenheimer approximation, what you can do is basically to look at what is the Born-Oppenheimer energy in terms of the position of the ions. And basically, if you want to reach the ground state of your system, what you will need is to minimize this in terms of the atomic position and identify what are the equilibrium position for this. Okay, so if you want now to solve your electronic problem, and again, here my capital R positions are implicit parameters, and I drop them in the notation here. But if I now want to solve this, it's still a quite complex problem because my electrons are correlated particles. So I need to know the many-body wave function here. So if you want to solve this, you can either try to solve the Schrödinger equation here, or you can use the variational principle, which tells you that you can get the ground state energy and wave function of your system simply in minimizing the expectation value of the energy in terms of the many-body wave function phi here. And this is related to the fact that the expectation value of an operator can never be smaller than the lowest eigenvalue. And so if you minimize this, you will find the ground state energy of your system. No, because I have three terms here: kinetic energy of the electrons, interaction of electrons together, and interaction between the electrons and the ions. In this Hamiltonians, I have three parts as well. I have the kinetic energy operator here. I have an operator of interaction between the electrons and an interaction between the electron and the ions. Now, if you make the exercise of calculating what these expectations values are, you will see that for the kinetic energy, basically you still need to know what is the many-body wave function, because you have a differential operator acting on that. Now, if you look at the interaction between the electron and the ions, basically the ions are defining an external local potential acting on your electron. So basically this term here basically depend on the many-body wave function, it can be easily recast, in fact, in terms of the density associated to this wave function. So basically this term does not need to know explicitly the many-body wave function to be evaluated. It can be estimated from the only knowledge of the density. Then you have the interactions here between the electrons together. And of course, this interaction is an electrostatic energy. So basically, you have an electron somewhere, you have another electron here, and they are interacting through a Coulombic interaction. So we could say, okay, let's look at what is the electronic density and estimate basically the electron-electron interaction through what we call the R3 energy, which is basically the energy that is computed by integrating over a space the interaction between the density we have at R1 and the density that we have at R2. And this is basically an electrostatic energy. But when we are doing that, we are making a mistake. Of course, we are making a mistake because here I can access the density of my system everywhere. But if I know that I have already some electron in R1, I cannot recover this electron in R2. And when I am evaluating this term here, basically, I am assuming that the density in R2 is independent of the density in R1. So in principle, I need to correct this term by what we call the exchange correlation energy here, which is basically the interaction of the electron that I have in R1 with what I call the exchange correlation hole that I have in R2. Basically, in this term, I have assumed that I have a given density in R2. But if I know that I have an electron in R1, then this electron won't be in R2. And this exchange correlation hole here is telling you what is the change of density in R2 when you know that you have already an electron in R1. Of course, this exchange correlation hole integrated over space will integrate to -1, the electron that is in R1. But then the way the density is modified when you have already an electron in R1 is something that is a priori unknown, and that requires basically the knowledge of the many-body wave functions. So basically, the electron-electron interaction is made on the combination of two terms, an R3 term that is some kind of classical electrostatic interaction between the electrons, naively obtained through this expression here, that depends exclusively on the density, plus a correction that is what we call the exchange correlation contribution to the electron-electron energy, and that is the interaction of the density with an exchange correlation hole. Okay, so if I want now to recast my problem here, I see that at the many-body level, if I want to access the ground state energy of my system, I need to minimize an energy functional over all possible many-body wave function. And this energy functional is made of different terms: a kinetic energy, an R3 energy, an exchange correlation energy, an energy of interaction with the nuclei. And interestingly, some of these terms depend only on the density, but some of them requires explicitly the knowledge of the many-body wave function. And so for years, people were asking themselves, so is it a way to avoid this many-body wave function? And the answer came from the Owenberg and Kuhn theorem, and that was published in 1964, where I won't, of course, go through the demonstration of this, but what they were showing is that there is a one-to-one correspondence between the external potential in which the electrons are, so basically this Vx that is here, and the ground state density. So that, of course, when you fix the external potential, you fix your Hamiltonian. And when you fix your Hamiltonian, basically you define all the properties of the system. So when they were showing that there is a one-to-one correspondence between this external potential fixing all your Hamiltonian and the ground state density of the system, it means that in principle, no, instead of defining everything in terms of the external potential, you can recast everything in terms of the ground state density. There is a one-to-one correspondence between the external potential and the ground state density. So anything that can be deduced from the external potential can similarly be deduced from the density itself. And basically here, this object is much more simpler than the many-body wave function. The many-body wave function depends simultaneously of the position of all the electrons everywhere. This density n of r is just something that is defined by a scalar quantity in each position in space. So that would be a great thing if we could express everything in terms of this simple object. And that's basically the key point of density functional theory. And I have recast it here in terms of the minimization principle, where you see that in principle, what I need to do is just to make a minimization of the energy functional here in terms of all the many-body wave functions. But I can do this minimization in two steps. I can say I will minimize over all possible densities, and then for each of these densities, I will minimize over all possible wave functions that are giving me this density. Okay, I can do this, but then if I do this, I need to minimize over the wave functions that give me a given density, these three terms here. And you remember that the last term here only can be cast in terms of the density itself, since it is corresponding to this thing here. So you see that this term here is totally independent of the wave function that give you a given density n of r. Only the density is important. So thanks to that, these terms can go out of this minimization, and I can recast this energy here as a minimization over the density of this term here, plus a minimization over all the phi that give me a given density of these two quantities here. Basically, what the Owenberg and Kuhn theorem is telling us is that in the same way this depends only on the density, if everything can be recast in terms of n of r, then basically this quantity here also must correspond to a given functional of the density. And this basically corresponds to the Owenberg and Kuhn functional, which, as you see, and this is a very important point. So basically, Owenberg and Kuhn said that basically the energy can be recast into the minimization of two terms here, and these terms that involve the external potential, and this Owenberg and Kuhn functional here. But this Owenberg and Kuhn functional that is appearing here, you see it only involves the kinetic energy of the electrons and the electron-electron interaction. So basically, this term here is totally independent of the external potential. So it means that it is a universal functional of the density. Universal in the sense that it must be the same functional for all solids that you study. So this is a very important point. So the Owenberg and Kuhn functional is a universal functional of the density. So it will apply to systems with different external potential. But of course, this theory was not very popular until many years later, because this functional is unknown. So this is basically a proof of principle, but there is no way to know what is this Owenberg and Kuhn functional at that time. So there is no practical way to make this minimization here. So the next step was just, can we find a way to know what is this Owenberg and Kuhn functional? And the answer came 1 year later in the famous paper of Kuhn and Sham, published in 65, where they proposed to use an auxiliary system of fictitious non-interacting particle that is built in order to produce the same ground state density as the interacting electrons. But thanks to this auxiliary system of non-interacting particles, you can write the density as the sum of one body wave functions. And if you know the density in terms of one body wave functions, then you can estimate what is the kinetic energy associated to this one body wave function. And this energy is what I call here Ts of n. And then, of course, if you remember what I said before here, when I was looking at these terms here, I was taking this term out of the minimization here because I was telling you, okay, this term here is only dependent of the density. But I forgot that in this term here that is appearing here, there are also two parts. There is the R3 part and there is the exchange correlation part. And the R3 part is also dependent only on the density. So the R3 part can also go out of this term here. And so if I take this into account, I can start from the Owenberg and Kuhn functional. I can put out of it the R3 potential here. I can take out of it the kinetic energy of the non-interacting system that I am now associating to my interacting electron, and defined a new functional here that I call the exchange correlation density functional. And then I can rewrite my energy here in terms of 4 terms. You would say it's the same that what it is here, but these terms are a bit different. You see that I have now a kinetic energy here of the density, but that can be estimated from the density, knowing that this density is associated to one body wave function. I have here an R3 term that depends only on the density. I have the interactions between the electrons and the ions that depends only on the density. And I have here an exchange correlation term that from the Owenberg and Kuhn function theorem should also depend only on the density. So what is the key part of the Kuhn-Sham ansatz is to replace the Owenberg and Kuhn unknown functional by another unknown functional that is the exchange correlation energy EXE of n, that is this functional minus these two parts. This is still unknown, so you might think, okay, so what was the purpose of doing that? The purpose of doing that is that in this functional here, this is a very big quantity. So this is the main part of the energy of your system. When you extract these two things, then you get something here that is now becoming a very small contribution to your energy. And so if you make a correct estimation of this, or even if it's an approximation, okay, you will still get something that is very reasonable to some extent. Okay, so what do we do when we do density functional theory? Basically, what we do is the minimization of an energy functional that is done now in terms of one body wave functions, and we need to minimize an energy functional that is including 4 terms, that all of them can be in principle expressed in terms of the density, a kinetic energy of the non-interacting particle, the R3 energy associated to your density, the interaction of your density with the external potential created by the ions, and the exchange correlation energy that depends on your density, and which is unknown and must be approximated. I will come to back in a minute. But minimizing things in terms of psi is basically equivalent to solve what we call the self-consistent set of Kohn-Sham equation. You just need to take the derivative of this expression respect to psi, and you will end up to this kind of equation here, where you see that minimizing this is equivalent basically to solve a one-body Schrödinger equation in which your fictitious non-interacting particle described by the wave function psi here are in an external local potential that I call here the Kohn-Sham potential, that is not only the external potential created by the ions, but is a self-consistent potential that includes, of course, the external potential created by the ions, but also takes into account the presence of the other electrons through the so-called R3 and exchange correlation potential. And you see that here you need to solve an equation where the potential depends, in fact, of the density that itself depends on the wave function, so that typically when you want to solve this problem, you need to solve these 3 sets of equations self-consistently. You start from given arbitrary wave function that provides you the density. From the density, you can estimate the R3 and exchange correlation potential. From this, you know the Kohn-Sham potential, and you can solve this equation, get an updated wave function here that allow you to update the density and to solve the problem self-consistently. So I want to notice 2 things here that are good to know. The first one is that I defined here a functional that is the exchange correlation energy that I wrote EXE of n. And this exchange correlation energy appearing in density functional theory is not the same as the exchange correlation energy appearing in the many-body problem. If you look carefully, you see that here I had a term that I call EXE of phi. Now I have a new term here that is EXE of n. But in these 2 equations, I have a different kinetic energy here. So it means that in density functional theory, basically the exchange correlation energy is the many-body exchange correlation energy, but in which part of the kinetic energy has been transferred. So basically, I can only estimate the kinetic energy of the non-interacting particles that is not necessarily the same as the real kinetic energy of the many-body particles. And so this small difference is globally included in the exchange correlation energy at the DFT level. So it's just a notice. And another thing that is important to notice when you do density functional theory is that you might say, okay, I have independent particles here, so the total energy of my system is simply the sum of the energy of this independent particle. No, when we do this, we really access the total energy of the real electrons, not of the fictitious particles that allow us to do so. So basically, the total energy that we compute is not simply the sum of the eigenenergy of the independent particles, but it includes some corrections here. So basically, the auxiliary system of non-interacting particle that is put here is just a trick to access the total energy, but within density functional theory, as you have seen from my construction here, I am really accessing the same energy as the one of the many-body problem. It will be exactly the same if I know what to put here. And this, of course, is unknown. So in principle, I would get the right ground state energy and the right ground state density of my system doing density functional theory, as long as I know the exact exchange correlation energy functional I have to put here. So in that sense, DFT is an exact theory, but in practice it is not, because this is something that we don't know. And so the next step is to find an approximate functional. And as I told you, and this is very important, EXE should be a universal functional of the density everywhere. So it's a universal functional. So I might not say, okay, there is one functional for one material, another functional for another material. No, I know it is a universal functional. But the complexity is that it should depend a priori of the density everywhere. So it can be a very non-local functional. In practice, usually this exchange correlation energy is assumed to be a simple quasi-local function of the density. And for instance, you heard probably about LDA or GGA, local density approximation, generalized gradient approximation. These are very simple approximations that typically allow us to make this density functional theory a practical tool. If I look at the local density approximation, it writes the exchange correlation energy functional of the density as an integral over space of n times an exchange correlation energy density of the homogeneous electron gas at this density. So it means, in other words, that the exchange correlation energy will depend on the density everywhere. But I assume that I can look at the density at each point separately, and that for the density at each point, it's not the same as the one I have at another point, but at this point, I assume that I have a given density, and that the exchange correlation energy produced by this density only depends on the density at this point. And so I assume that I can get this contribution to the exchange correlation energy from the one of the homogeneous electron gas. So I will assume that I know for homogeneous electron gas what is the exchange correlation energy in terms of the density. And then at each point of space, I will look at what is the density and I will multiply it by the exchange correlation energy of the homogeneous electron gas at this specific density. And then my density is evolving from point to point, and I will sum the different contribution. But this approximation is totally ignoring the fact that the exchange correlation energy here might be a non-local quantity. So that's why it's called the local density approximation. And it has become very popular because during the 80s, Seperle-Alder did some Monte Carlo simulation on the homogeneous electron gas, and they were basically quantifying what is this quantity here from Monte Carlo simulations. And so basically the different flavors of the local density approximation that you can find are basically different fits of the same Monte Carlo data of Seperle and Alder. Okay, so having something that only depends on the density locally might be a very strong approximation. It's amazingly good in many cases, but people were thinking, okay, we should try to do something better. And so people started to define generalized gradient approximation, where they kept basically the same spirit, but here they defined a quantity that does not only depend on the density locally, but also from its different gradients. And so that's why we call that generalized gradient approximation. And then you see there are two different flavors have been defined. And of course, you see this is like cooking. You see, you can invent many recipes and the ways that people spend their life to get a better functional. That's certainly not the purpose of this course to go through this. But usually we have to choose this, and defining the functional we will use will give us some level of approximation. Still, it's not because you move from LDA to GGA that we will necessarily improve the description, because you make an expansion here, you stop somewhere, but when you have an oscillating function, so you see, it's not, you are not necessarily improving when you go further. And that's something I will show you in a minute. So there is no strict rule to say, okay, this is the best functional. No, okay, we have to try and then to figure out what might be the most appropriate for our system. Of course, this is not working for everything. And there are many flavors to go beyond the usual functionals. One way is to do DFT plus U, in that we add a Hubbard-like U term to localize electrons. That's one way that is used in practice to address correlated oxides. We can also use hybrid functionals that are seen as basically a mixture between density functional theory and Hartree-Fock. Said like that, it looks like cooking. You see, you know what is Hartree-Fock, you know what is DFT, then you try to make a mixture to improve the things. There are some rational way to do that. And the idea here is to re-include in DFT a percentage of exact exchange in the spirit of Hartree-Fock. So of course, I have no time to explain all these different functionals here, but each time I refer to some papers that you can look at if you are interested. For the case of hybrid functional, I'm referring here to a paper we wrote 10 years ago, and in which we define a specific hybrid functional for perovskites. Then you can also go to other approaches that are called pseudo self-interaction correction, that basically try self-interaction correction or pseudo self-interaction correction that basically correct for the self-interaction in density functional theory. And then you have other more sophisticated approach like DFT plus GW that is not really a DFT approach anymore, but that do some perturbation theory on the Kohn-Sham eigenvalues. And then you can think about DFT plus DMFT as it is described in the lecture of Antoine Jean. I would say when you go in this direction of going beyond the usual functionals like DFT plus U or hybrid functional, automatically you have some kind of free parameters in your calculation. So it's no more, you would say, first principles. But then sometimes there are some specific way to determine what should be the self-consistent value of these parameters. And that's what we try to do. In this case, we have a U parameter. In this case, we have a mixing parameters, and we need to adjust that to something that we believe is realistic. What you have to realize is that when you start from basic DFT to more complicated approach, it becomes more and more difficult to do structural relaxations. I would say in GW or in DMFT, it's not so easy to define an energy for your system. So to make structural relaxation, you need to access the energy, and derivative of the energy respects to atomic position that provides you the forces that will allow you to minimize the energy in terms of the position of the atom. So this is not easy. There are some attempts, there were some attempts recently to do that, but it's very easy. And in practice, people work in this approach on a geometry that has been adjusted at the DFT level. Now, when you look at the functional that you have here, like DFT plus U or hybrid functional, it's still possible to do structural relaxation. It's quite natural in DFT plus U with all code. It's possible also with hybrid functional, although it becomes computationally very easy to do relaxation with hybrid functional, except with some code like Crystal that use Gaussian functions. But so typically also people try to avoid relaxation with the hybrid. Hybrid, I think, is very important in the sense that they can correct the band gaps. And so when you look at heterostructures, they are very important to properly adjust the band offset at the interface. And that was the purpose for her to define a specific hybrid functional for perovskite at that time. Here, DFT plus U is required for different materials like the nickelate I will discuss later, and that are not properly described in LDA or in GG. Okay, but I would simply mention here that, okay, these tools that I have just presented have strongly evolved since the 90s. So DFT really started to become popular in 1990. There were already many advances during the 80s. And then during the 90s, people were really starting producing results on more and more complex materials. Nowadays, there are professional codes available that you can access. Some of them you need to pay. Some others, like Abinit, are totally free. And it's good to realize that this method has now acquired a very high precision and a reasonable accuracy. So what's the difference between precision and accuracy? So precision is the kind of dispersion within the result you get when you use different codes or different techniques. And you see that historically, there was a broad discrepancy even between different codes. Nowadays, if you compute a quantity using VASP, Fiesta, or Abinit, basically you will get more or less the same number. So it's like when you do an experiment, if you use a microscope in Geneva, or if you use the same microscope in Liège, in principle, you should see the same thing. Nowadays, it's the same with first principle codes. Even if they rely on different approximations, different bases, different things, still no, they all more or less converge to what we call very precise numbers that are the same for all codes. Of course, it doesn't mean that this number to which we converge is the experimental value. This is another story, and that's what we call accuracy. But in many cases, we have a reasonably good accuracy, and that's what I will describe now with you. So what do we do when we perform a first principle simulation? Basically, we use periodic boundary conditions. So we work under zero electric field. And basically, the ground state that we need to reach is the minimum of the Born-Oppenheimer energy that, in other language, would correspond to the internal energy of your system. And so doing a calculation is basically requires to do two loops. Basically, you choose some starting geometry. So you fix R, and then if you fix R, you fix the parameter here in your Born-Oppenheimer Hamiltonian, and then you need to find what is the electronic ground state. And so you will minimize over the different wave functions in order to get what is the Born-Oppenheimer energy at this geometry. And then from this, now you will, thanks to the Hellman-Feynman theorem I will mention later, you can identify what are the forces acting on the atoms at this level, and you will be able to move the atoms and step by step reach the minimum of the Born-Oppenheimer surface. So basically, there is a first minimization over the wave functions performed at fixed ionic positions to get this Born-Oppenheimer energy in terms of R. And then you need to make a second external loop in order to minimize over the atomic position in order to identify the ground state of the Born-Oppenheimer energy here. Okay, and so when we have that, what do we learn? We can access to the total energy of the system. So it means we can access cohesive energy, relative stability of different phase, surface or interface energy. We can perform structural optimization. So it means that we can get cell shape and size. So what is my unit cell? What are the atomic position within the unit cell, the bond length, the bond angles? These are the structural, I would say, properties. And we can also access some electronic properties. So we can make some electronic density plots like here for biome titanate. We can access the atomic charge, the magnetic moments. We can also plot the Kohn-Sham electronic band structure, although we should keep in mind that there is no formal link to the real band structure a priori, because the Kohn-Sham band structure is the epsilon I mentioned before. So basically the eigenvalue of the fictitious system of non-interacting particles and not the eigenenergy of the interacting particle. And that's really the purpose of GW, is to move from this to the real things. But in practice, it's common to compare and to look at the Kohn-Sham electronic band structure because it has already features very close to the band structure of the real electrons, the main discrepancy being the band gap that is not properly described due to a discontinuity of the exchange correlation energy that is not properly taken into account in the usual functional. So, but for these quantities, typically we acquire an accuracy of 1–2%, except for band gaps of cohesive energy that are usually not good in LDA or GGA. If I look more specifically at the latest parameters in perovskites, that is the materials we are interested in here, you can go to this book, Physics of Ferroelectrics, edited by Jean-Marc and other people, where we see that when we look at different perovskites in their cubic phase and at different functional, we see that we have reasonable accuracy with the conventional methods, although you can keep in mind that LDA underestimates slightly the volume, while GGA often overestimates it. And you will see that there are some lucky cases where one of the functional provide the right thing, but typically the trend is this one. So this is for the cell parameters. Now, if we look at the atomic distortion, here I am comparing the atomic distortion that we have in the ferroelectric phase of biome titanate and lead titanate, so in the ferroelectric phase. So what is the distortion between the paraelectric cubic phase and the ferroelectric phase? The atoms will move following to a given pattern. And here I am just doing this relaxation of the atomic position, but at different constraint of my unit cell. The theory one refers to the one where I keep the experimental volume and cell parameters. The theory 2 corresponds to the case where I relax simultaneously the unit cell and the atomic position. And the theory 3 and 4 are the same, but where I keep basically a cubic unit cell. So I'm not allowing the cell to become tetragonal if I go to the tetragonal unit cell, for instance. And what you can see, we should analyze this more carefully, but the message is that we get similar results in LDA and in GGA if we work at the experimental volume and experimental unit cell, which means that basically the mistake we make on atomic distortion in the LDA comes mainly from the fact that the volume is underestimated in LDA. We underestimate the volume, and so when we look at ferroelectric distortion that is very sensitive to the volume, of course the LDA will also underestimate the polar distortion. But if we put some kind of negative pressure by keeping the experimental volume, then we recover some kind of good distortion. Of course, here I'm saying that we underestimate the polar distortion. It means that we could also overestimate the antiferrodistortive motion, because the antiferrodistortive motion just has the opposite sensitivity to volume. When you have a smaller volume, you amplify the oxygen rotation, and so you typically see that trends also in perovskite. Another point that is good to know, and just to illustrate that GGA is not always better, if we look at GGA PBE for ferroelectrics, you realize that in many cases it is wrong, and this is illustrated here, where you see on this line here, this reference. You should go to the book to see what is this reference here. But you see that when you do a relaxation of lead titanate or barium titanate in GGA PBE, you go to a super tetragonal phase that is totally unphysical. So in some cases, some functional are not working, and it's very difficult to anticipate that in advance. I like to mention here that even for more complex systems like yttrium nickelate, DFT, here it's DFT plus U, but DFT plus U, so I would say very standard approach, can produce a very good comparison with the experiment. You see here I'm comparing the lattice parameters and atomic distortion in yttrium nickelate in the ground state P21N phase with the appropriate AFM E prime order. You see when you compare the lattice parameter, you get incredible accuracy within the experiment and the simulation. And when you look at the amplitude of distortions here, also you get something very good. So it means that DFT can be good even for this kind of apparently strongly correlated materials. Of course, you need to use a U, and this U, of course, will change more or less the accuracy. I'm just here mentioning the relative deviation we get for the lattice constants and the amplitude of the mode where we tune the U parameter. You see that in this regime here, all the distortions are properly described. If now you increase the U, you see that the breathing distortion in this material will be strongly affected, and it can be overestimated by 100% if we don't use the right U. So there is some degree of freedom, of course, when you do DFT plus U, and you need to find what is the U that gives you the right agreement with the experiment, which is not fully first principle, or you might also try to compute the U self-consistently, and when you do that, you see that you are in this appropriate regime here. So this is when you are in zero field. Now you can also imagine that you work in finite electric field, and in that case, the quantity that you need to minimize is no more the internal energy of the system, but the electric enthalpy. And that can also be done using DFT method. So instead of considering the internal Born-Oppenheimer energy of your system, now you need to define an electric enthalpy that is E minus E dot D. And so this is the new functional you need to minimize. But this can be done, and you can even do with code like ab-init calculation under finite electric field, where instead of minimizing the Born-Oppenheimer energy, you minimize this functional. You just add basically two terms that give you the energy of the field and the coupling energy between the field and the material. And now when we work with periodic solid, you can also separate the strain and ionic degrees of freedom. And then instead of referring to capital R, you can refer to capital R and strain and get an expression that where these internal degrees of freedom are separated into things. I want to mention this just to show that the physical quantity that basically now when we have this energy functional here, that is the internal energy or the electric enthalpy, that depends of different parameters here. Now we can make an expansion by looking at how it's evolved in terms of the amplitude of that. And so we have a reference configuration, and then we can look at what is the change, what is the energy at finite value of this parameter as the one in the reference configuration, plus the derivative of F respect to the field times E, derivative of F respect to atomic positions times atomic distortion, plus the derivative of F respect to strain times the amplitude of the strain. We can do that, make this expansion at first order, second order, third order. And what is very interesting is to realize that the different quantities, the different energy or enthalpy derivatives that are appearing in this expression, basically they correspond to physical quantity like the polarization, the force, the stress, the dielectric constant, the Born effective charge, the elastic constant. And so basically many physical quantities are related to successive derivative of the energy. And so these quantities are also accessible through a perturbative approach in density functional theory. So there is density functional perturbation theory that has been developed. And then from this, we can access the derivative of the energy either by finite difference or using a perturbative approach, using either a variational expression or solving a self-consistent set of Sternheimer equation. Basically, these two approaches to minimize a functional as we did in DFT before, or using a set of Sternheimer equation that is basically equivalent to solve the set of Kohn-Sham equations. And in these cases, we can access the derivative of the energy, and so these physical quantities. Knowing the first order wave function, we can not only access the second derivative of the energy, but even the third derivative of the energy, because there is a 2n plus 1 theorem that teaches us that the derivative of the energy up to order 2n plus 1 can be deduced from the knowledge of the wave function up to order n. And so if n here is 1, you see that you can not only access E2, the second derivative of the energy, but you can even access E3, which means third derivative of the energy. And so this means that usually from density functional calculation, you can access first order derivative like force, stress, polarization, second derivatives like optical and static dielectric tensor, elastic constant, Born effective charge, phonon dispersion curves, but even third order derivative like nonlinear susceptibilities, Raman intensities, electro-optic coefficients, and so on. So for these quantities, of course, the accuracy decreases when you increase the order of the derivative, but typically as second order, we get an accuracy of 5 to 10%. So I just want to show you here, for instance, in terms of phonons, I'm reporting here some phonon dispersion curves. So this is a plot I made during my PhD regarding biome titanate in the cubic phase. I will come back to that later, but basically I have unstable phonons here that basically are stabilized in the cubic phase at high temperature. But you see that for most of the branches, at least the low frequency branches, I get a dispersion from my calculations that are very close to the experimental measurements that corresponds to this cloud of points here. If you look here at bismuth ferrite, we did also compute the phonons in the R3C phase of bismuth ferrite. It's a very basic calculation, NDA, optimized volume, and you see that it fits very nicely with the experimental measurements that are reported in this journal. Here I'm just reporting the Raman spectrum of lithium niobate. You see, this is the experimental spectrum. This is the computing spectrum. And you see that there is a very good correspondence. It's not always perfect, but you can really assign the experimental peaks from the calculation. So typically, we are making a good job in DFT for the structural properties. So now there are two last things I would like to mention. Is that the phonons that I've just shown are very well reproduced in DFT. They form an alternative basis to atomic displacement. So usually you are used to write the Born-Oppenheimer energy through the harmonic approximation by saying it's E0 plus 1/2 the sum of the interatomic force constant times the product of the displacement plus other things here. And here, basically, you have 3n degrees of freedom that are basically, you can imagine that the Born-Open energy depends on the position of individual atoms that you can move individually along X, along Y, and along Z. Now, to this atomic displacement, you have phonons that are associated to that. That's the eigenmode of vibration of these atoms. So these are collective motions, but again, the phonons form, the number of phonons corresponds to the number of degree of freedom of your system. So if you n atom that can move in 3 directions, you have 3n degrees of freedom. And to this individual displacement of n atoms in 3 directions, you will associate 3n eigenmodes of vibrations. And this eigenmode of vibrations, they are orthogonal to each other. So basically, they form also a complete basis for the description of the displacement of your atom. So basically, you can take your Born-Oppenheimer energy, and instead of explaining it in terms of atomic positions, you can make a rotation to the phonon basis and write it in terms of the amplitude of the distortion of the atoms produced individually by each phonon mode. And if you do that, you write it in this way, you see that while here different atomic displacements were coupled together, here you get a set of independent harmonic oscillators. That's what allows you later to introduce the concept of phonon. But what is very interesting in this expression is that when you work in the basis of the phonons, basically you see that the omega square here, the phonon frequency square, corresponds basically to the curvature of the Born-Oppenheimer energy along the path of distortion defined by the phonon eigenvector. So if I plot the Born-Oppenheimer energy and I move the atoms following the eigenvector of a given phonon mode, the curvature I will get for the energy here will correspond to the square of the frequency of the mode associated to that eigenvector. So this is very interesting because you see that if you have an energy surface where the curvature is positive, then omega square will be positive and you will get a real phonon frequency. But now when you have system where at some points you have negative energy curvature, it means that omega square will be negative. And so when you will solve your dynamical problem, you will find negative eigenvalue in your dynamical matrix that are associated to imaginary phonon frequency. This imaginary phonon frequency are not something that is crazy. It's simply telling you that there is somewhere a negative curvature. And so this allows you to identify structural instability in materials. And if you take the cubic phase of barium titanate, if you compute the phonons in this cubic phase, you will see that you have a bunch of stable phonons here at real frequency. And here below 0, I reported imaginary frequency. And you see that there are some modes that have imaginary frequency. This is telling you that this cubic phase is not stable. There is some way, some path to follow along which you will decrease the energy, and it is the fingerprint of a structural instability. So basically, I think it's very important to work, it's interesting to work within the phonon basis, and I just simply showed you what it means in a simple molecule here. You see, when I have two atoms here, I can imagine I have a chain and these atoms are moving along X. I can describe the motion here in terms of individual atomic displacement. That would be the usual way, and that's what I call the atom basis. Now I can work also in the phonon basis, where I will define two modes, one where the two atoms move the same way, one where they move opposite way. These two motions are orthogonal to each other. Now, when I have a distortion of this molecule here, that corresponds to a point somewhere, I can express it in this basis here, in terms of given amplitude of U1, given amplitude of U2, but I can also see it as a given amplitude of eta 1 and another amplitude of eta 2. And that's what I working within the phonon basis. I will say that reaching this point here means that I have activated the first phonon with a given amplitude and the second phonon with another amplitude here. And you see these two bases are equivalent, but working within the phonon basis, we will see later, is quite interesting. And when I work within the phonon basis, something I can do is just to understand better the distortion. And I told you before here that it happens in some materials that I have an instability, and then I will go from a high symmetry phase to a low symmetry phase here. But when I am here, I have put some distortion in my material. And so when you have a reference and a distorted structure, it's often convenient to look at the phonons in your reference structure and then to look at the distortion that appeared between these two structures and to project this distortion here in the basis of the phonons corresponding to this structure. In other words, you write this distortion of the distorted structure as a sum of distortion produced by the different phonon modes of the first structure. So you see, for instance, I have a distortion here that corresponds to the motion of the atoms from here to here. And then I will project this over the basis that is formed by the phonons of this reference structure here. And I will say it corresponds to this displacement, this collective motion associated to eta 1 with this amplitude plus this with those amplitude. Since these phonons form a complete basis, any distortion can be expressed in this basis. And then I can understand the distortion here as the superposition of the distortion produced by the activation of different phonon modes. This is very important for second principle because it allows us to identify all the relevant phonon modes involved in the transition from the reference to the distorted structure. And then because each phonon has a given symmetry, we know the way these modes will couple together. Due to the symmetries of the modes that are involved, we know that they can only couple a given way. And we will see that this is very important to build second principle model and to achieve the terms of these second principles model properly, because we know that in the expansion of the energy, only some terms are possible. Okay, so in summary, first principle, DFT and related methods nowadays are a standard and useful tool to explore on the Born-Oppenheimer surface. They are still limited to small system and short time scale. And in practice, basically, they are restricted to 0 Kelvin. So basically, the next question I want to address is, can we achieve larger scale description and model structural phase transition? And that's basically the second part of my talk, where I will try to convince you that it's possible to do second principle. And the idea is, how can we get simple model for structural phase transition? And then I will go through different kind of approach. So if we want to describe a phase transition, we have first to realize that the phase transition is identified thanks to what we call an order parameter that I will call P here, the parameter. which basically is a physical quantity that switches from 0 to a non-zero value at the transition. And typically, so this must be identified, of course. And then when you know what is your order parameter P, the Landau theory is a thermodynamical approach that tell you that the stable structure is the one that minimizes the appropriate thermodynamical potential. So for instance, if I am interested in temperature phase transition with free mechanical boundary condition in zero field, the thermodynamical potential I need to minimize is the free energy F is U minus Ts. And the basic idea of Landau is that F can be expressed around the transition as the power series of the order parameter. So basically, I will express the free energy as a polynomial expression, expansion of F in terms of P. I put here the simplest possible case, probably you know that already. And what is interesting is that the expansion around the high temperature phase should remain valid above and below the transition. So it means that this expansion is the same when you are above and below. And also it means that the expression that we get for the energy here, or for the free energy, of course, if it applies to the high symmetry and the low symmetry phase, it should respect the symmetry of operation of both phases. So Philippe? It means that basically when you...
Philippe?
Hello?
This is Manuel. So yes. I think you're running a little bit late, and I just wanted to ask you how long do you need to finish?
If I don't finish today, I finish tomorrow. So I was not planning anything. So we are on time. So it's finished for today, or?
Yeah, I think you expire your time. Maybe you should have stopped at before starting the second principle.
Okay. I didn't look at my clock, so but I can stop. There is no problem.
So I am asking Mark. So we should stop here. Yeah.
Yes, yeah, I think it's better because we have to we have people from Asia, and also let's keep the timing, and I would say it's a natural transition point for your lecture. So tomorrow you can continue, and now Manuel can direct people who have questions to ask, and we'll see tomorrow. I mean, normally you have 75 minutes tomorrow, but if it looks like there are less, questions that will not require 45 minutes, then you can go on for a little longer. Let's do it that way.
Yeah, I realized I was a little bit too slow today. I wanted to do a little bit more, but anyway, I think I will adjust tomorrow to reach the final part of the talk that is basically the most, probably the most interesting. But I thought it was important also just to put back the concept so that we know what we are doing, because there are many subtle points that I mentioned today that will reveal quite interesting tomorrow. So, okay. So I'm ready for the questions.
Okay, thank you very much, Philippe. So I don't think there are a lot really questions in the chat. There's someone who is asking if in the next lecture you will talk about domain formation.
I won't speak today about domain formation.
Tomorrow.
Tomorrow. No, I won't speak tomorrow about domain formation. I will stay at a quite formal level where I will try to explain how we can build simplified model. And I think it's, you see, when we do a first principle simulation, we consider basically all the degrees of freedom together. And then we have a description, but that is just like a black box, you see. I put some ingredients, then I do a calculation where everything is there, and I see some behavior. Okay, so I'm just, thanks to DFT, mimicking basically what nature is doing. And one point is to try to get techniques that provide the right description. That's what we want to do from first principle. But sometimes when you do first principles, you get a result, but you don't understand why you get that result. I would say the construction of models is very useful just to be able to identify what is the minimum physics that will bring you to the point where you are. And in that sense, basically, there is some feedbacks between first and second principles. On the one hand, to identify what are the relevant degrees of freedom to be put in the model, and reciprocally from the second principles to tell what part of the first principle result is important to the physics and what is maybe meaningless. So tomorrow I will mainly focus on how to extract the meaningful parameters from DFT to build the second principle models and what we can learn from this second principle model. But I won't have time to do many illustrations of domain wall formations. These are very specific cases. So I can, of course, refer to some literature on that. What can we learn from second principles to address domain wall formations? There are very nice papers by Javier Junquera, for instance, not only domain wall formation, but also formation of skyrmions or ferroelectric bubbles or these kind of things. I don't know exactly if that was part of the question, but of course, if the student who is interested in that send me an email, I can provide some good reference for discussing that. I
think it should be made public, Philippe, so that everybody can take advantage.
Oh yes, I have no problem.
No. I mean, it's just the idea of the school. So if someone is asking a question which can be of interest to the community, I think it's good that it's being shared.
Is there any website? Because of course I cannot provide such a reference. You see, online. No, I have to look. I would say that also the spirit of this school was to be together for 1 week.
Sure,
chatting together. So maybe we could continue to chat offline. Not necessarily offline, but just to have some time to adjust. Then
sure,
I can answer publicly, of course.
Yeah, but tomorrow you will have your second lecture, and so at that point the student will let's say ask the same question again. You will have had time to
exactly
to look at the reference, and then you can provide it.
Yeah. I can include them at the end of my PowerPoint.
Yeah.
I think probably if you go, but no, these are probably not totally related to. Here I mentioned some work, if you can see, but that's not the most, I would say, descriptive papers of domain wall formations, but they are exploiting what they can do from second principles to predict domain wall formation here in PTO, STO superlattices. Just to anticipate the effect of negative capacitance in some superlattices. But I would say the physics, I don't know what, also if the question was about domain walls in ferroelectrics or in other materials, because of course there are many types of domain walls. So that's maybe the first question I should ask to the student. Was it ferroelectric domain walls, or was it some kind of ferroelastic or electronic things or whatever? Because I don't know.
So
the student,
maybe Gal Tuvia, you can turn on your mic and ask directly the question to Philippe. Hello.
Hello.
Yeah, please go ahead, ask your question.
Hi, can you hear me?
Yes.
Yeah.
Hi. So yeah, I was asking specifically about STO. My group recently published this article about the calcium-doped STO LAO interface, where we think there is some interaction between in the interface between the LAO and the ferroelectric calcium-doped STO. And we believe that domains near the interface have some effect, that they feel somehow this interface. And I was just wondering, we have some experimental results in some very simplified model, but I was just wondering if I can have more information on this topic, just to maybe try making this model a bit more, how do you say, less simplified, and maybe have more ideas for other experiments we can try. Thank you.
Okay. Can you hear me?
Yeah.
Yes, yes.
No. Okay, so I think when you look at the figure I've mentioned here, and that's the point, that's basically what happens when you create an interface here. It's mainly the electrostatic coupling between the layers that play a very important role. So if I try to explain a little bit the figure that we have here, when we have PTO, STO superlattices, for instance, you have here a material that wants to be spontaneously ferroelectric. So in principle, it wants to polarize. While on the other hand, here you have a material STO that is a priori non-ferroelectric. And so it means that if you want to polarize basically the PTO here, and you imagine that you cannot polarize the STO here, basically you will accumulate some charge here at the surface. And if you polarize up, for instance, here, so you will accumulate some positive charge here, some negative charge here. And if you have no screening of this charge, you will get a huge depolarizing field that will kill the ferroelectric instability in PTO. And that's what you would expect for a film that is without any external screening. And so this is something that is very well known in ferroelectric. So the monodomain configuration will be unstable without some screening of the surface charge. And so the way the system finds to solve this is just, you see, by breaking into domains, so that you will have, you see, positive and negative charge, so that on average you will have something that is neutral here. But so, of course, depending on the way you can screen the polarization at the interface here, you can get many different things happening here. And if you look, like, for instance, at PTO, STO, what will happen in the PTO layer will strongly depend also on the STO thickness here, because STO here is something very specific in the sense that it's not ferroelectric, but it has a very large static dielectric constant. So you see STO as a dielectric constant at room temperature that is around 300. If you go to low temperature, it will become even much larger. So this is a highly polarizable material. So it means that producing a polarization in STO is not so costly. So you can imagine also that in some configuration here, this layer will polarize as the PTO here, so that you will get a full polarization through the whole stack here. Of course, polarizing STO requires some energy, sorry. And of course, the thicker the STO, the more the energy you will need to provide to polarize a thick layer. And so, depending on the relative thickness of PTO and STO, you can see different regimes that are due to the fact, is it better for the system to be homogeneously polarized in all the layers, which is one possibility, or is it energetically more favorable for this layer to be non-polarized and this one not polarized either? So you will eventually even reduce the polarization here. Or is it better for the system to stay fully polarized, but by developing domain, knowing that there is also an energy cost associated to the domain work. And so it's really different energy contribution that will balance each other's, and depending of the relative value of the different terms, you will favor one configuration respect to the other. And that's basically what this kind of second principle modeling is doing, is just taking into account these different energy contribution, okay, the energy cost associated to the displacement of an atom here in the central layer, the displacement of an atom here, and then see basically at the short range level, at the electrostatic level, what is the most stable configuration. So, okay, if you have another system, I would say we should explore basically the different possibilities offered to the system to develop the polarization and try to figure out which one is the most stable.
Okay, thank you very much, Philippe.
Thank you.
So I think we have to leave it here for today. Thank you very much for being here with us. Thank you, Philippe, for the very interesting talk. And so I think the next talk this afternoon will be given by Antoine Georges again. And so I invite you to join us again at 4:30. Mark, do you have anything else to add?
No. You said you gave the information I was intending to give, so that's great. So we'll meet again at 4:30 Paris time.
Okay. All right.
Okay.
Bye-bye.
See you tomorrow.
Bye-bye.
Bye.